Hello and welcome in this OpenFOAM tutorial. The simulation of 1D heat transfer and pyrolysis inside a solid material with a prescribed heat flux on the top surface will be considered. As such, only the solid phase will be simulated, not the gas phase. The tutorial is aimed at people who have some minimal experience and understanding of OpenFOAM. We will demonstrate how to set up the geometry, briefly go through the main required case files, and run a simulation. OpenFOAM version 1912 and the fireFoam solver will be used. The case consists of three folders: Zero, Constant, and System. Several scripts are also available for automating several processes when generating the mesh, cleaning, or running a case in parallel. We will examine some of these scripts later on. Let us first take a brief look at the most important files of this tutorial. The Zero folder contains the initial and boundary conditions of each variable used by the solver in the gas phase. Since the gas phase will not be solved, these files are less important here. However, what is important to examine is the sample region folder, which contains the initial and boundary conditions of each variable used by the solver in the solid phase. These variables include char, pressure, radiative heat flux, temperature, virgin material, and any other species. The most important file to examine is the one corresponding to temperature, where the heat flux at the top surface of the solid sample and the heat losses from the bottom surface of the sample are defined. Here we apply a 50 kilowatt heat flux at the top surface, while the bottom surface is adiabatic. Hence, no heat losses are computed. Note that a boundary condition where convective heat losses from the bottom surface with a prescribed convective heat transfer coefficient is also available for use. The constant folder contains all the required submodels used for modeling. The pyrolysis model in the solid region where 1D heat transfer and pyrolysis will be simulated is specified in the pyrolysis zones file. Another important file in this case is additional controls, where we declare that the gas phase will not be solved. Hence, only the solid phase will be considered. Finally, the sample region folder is also essential, as it contains files related to the solid phase. Here we define the radiation properties of the virgin material and char, see Radiation Properties file, the Arrhenius decomposition reaction and its parameters, see Reactions file, as well as the properties of the virgin material and the char, see Thermosolid file. The system folder contains the geometry and the mesh of the case in the gas phase, see BlockMeshDict file. The time controls, including the total running time of the simulation, and the time step are also defined here. See ControlDict file. The sample region folder relates again to the solid phase and contains files related to the discretization schemes. See FV schemes file. The tolerances when solving the equations. See FV solution file, as well as the decomposition method and the number of processors if a simulation is run in parallel. See decompose pardict file. Two more files are included. See toposetdict and extrude to region meshdict files, which are required for setting up the geometry in the solid phase. More specifically, in toposetdict, we define the size of the solid sample, while in extrude to region meshdict, we define the solid sample thickness and the number of cells along its thickness. We start by making the computational domain in the gas phase, even though the simulation will only consider the solid phase. The mesh in the gas phase is mapped on the top of the solid surface. Hence, it is still important to define it. Here we consider a rectangular domain with length and width of 0.1 meters, while the height is 0.0184 meters. Note that in this case, the height of the domain has the same height as the solid sample. See the extrude to region meshdict file presented earlier. This is not really needed, nor is it essential. The domain can have whatever height the user wants. We first define the 8 vertices of the domain. The numbering of the vertices starts from 0, hence they are labeled from 0 to 7. The starting point of our coordinate system is the center of the bottom boundary of the domain. To create the domain, see the BlockMeshDict file, we then define a block with these 8 vertices, starting with the plane defined by vertices 0, 1, 2, 3, and followed by the plane defined by vertices 4, 5, 6, 7. We consider an unstretched mesh with 50 cells in 2 directions and 10 cells along the height. Finally, we define the 6 boundaries of the domain, including their name, that is back, sides, front, type, that is patch, and the vertices which identify them. The solid surface is then created by selecting the faces on the bottom boundary of the domain, see the toposet dict file, and the surface is extruded outside the domain with a given thickness. See the extrude to region mesh dict file. There are 5 scripts available in the tutorial: clean, mesh, deck, run, and reconstruct. The clean script cleans a case. The creation of the computational domain, mesh, and the solid sample is automated through the mesh script. The script performs 3 operations, that is block mesh, toposet, and extrude to region mesh, automatically and in a sequential manner. The deck script decomposes the case to a user-defined number of meshes to be run in parallel. The run script runs a case in parallel, while the reconstruct script reconstructs the solid phase after a parallel simulation has been completed. This concludes today's tutorial. Thank you for watching the video. Don't forget to hit the like button, share, and subscribe.